Alright, we're back into section 4.5 where we've been doing some work with graphs of the sine and cosine functions. We looked at the graph of y equals the sine of x, y equals the cosine of x in an earlier video. And now we're looking at transformations. We talked about what happens when we have vertical stretches, and we just started talking about what happens when we have horizontal stretches or shrinks. And so let me remind you that when we have our two trig functions in this form, where a and b are real numbers, not equal to 1, not equal to 0, the amplitude of the functions is the absolute value of whatever this a value is, because remember, the amplitude for sine and cosine, the parent functions for sine and cosine are 1, and so we are multiplying by the absolute value of this number here. Remember, if these are negative, if a is negative, it's a reflection in the x-axis. The period, how the graph is affected horizontally, like an accordion perhaps, you know, stretching it out or shrinking it back in, or the old-fashioned accordions anyway, is determined by taking the period of the parent function, 2 pi, and dividing it by the absolute value of this constant that's times our independent variable x. So again, absolute value, because if b is negative, it's a reflection in the y-axis. But what we're going to do here is we're going to take this information and we're going to look to graph trig functions that are in this form. And I have an example right here. Given f of x is equal to 2 times the sine of 4x. In this case, a is 2 and b is 4. We're asked to identify the amplitude and the period. Well, the amplitude would be the absolute value of 2, which is 2. And the period, the fundamental period of this function, would be 2 pi divided by the absolute value of 4. 2 pi divided by the absolute value of 4, which is 2 pi over 4, which is pi over 2. Now think about this. If the period for the sine and cosine functions is 2 pi, and now we're looking at a variation of this in which we have a horizontal shrink so that it goes all the way to pi over 2, that means that our wave gets shrunk in, and it's going to be much faster. It's going to be up to 1 and down to negative 1 a little bit more quickly, or in this case, up to 2 and down to negative 2, because this is going to affect and be a vertical stretch. So I can do both graphs. Normally what I like to do when I first start out is I graph, in this case, the sine function. Then I graph this graph here of the sine of 4x, and then I go ahead and I do the 2 times that, because what happens is I'm doing it in stages. This is going to give me how the graph is affected horizontally, and then this takes that horizontally affected graph and stretches it out vertically because of this being greater than 1. So I'm going to kind of do it all in one step here by finding key points. Now, key points are where I have my intercepts, my x and y intercepts, primarily my x-intercepts, and I also have my highs and my lows, where my graph peaks and where it bottoms out. Now I actually put a few extra points in here, and if you're wondering, how in the world did you come up with these x values? Well, I'm remembering that I'm going to multiply whatever the x value is by 4. So I took key values and I divided them by 4 so that when I plug them into here, multiply by 4, I get, look at these guys right here, I get these values between 0 and 2 pi that are values that I have memorized. I have memorized my unit circle, so I have these memorized. And then I go ahead and I plug in. So for example, I just take one at random. Let's say I take 5 pi over 16, and I plug 5 pi over 16 into here. I now have, I'm going to put it right over here, it's going to be kind of squished. I'm going to have y equals 2 times the sine of 4 times 5 pi over 16. That's 16 there, believe it or not. Now when I multiply the 4 times the 5 pi over 16, it simplifies. I have 2 times the sine of 5 pi over 4. The sine of 5 pi over 4, it's one of those values that you should have memorized. Whether or not you do, you should have it memorized, is negative square root of 2 over 2. So when I multiply this, negative square root of 2 over 2 times the 2 in front, I get negative square root of 2. That's where this guy is coming from. I'm plugging them in and doing that. Now I went ahead and completed the table to save us a little time, but I'm going to go ahead and graph this using these x values and these y values. Now notice here also my scale. Each one of these little tick marks on the x-axis is worth pi over 16. It's not drawn to scale, as you can see, because pi over 16 is a pretty small number. It's less than a fourth. And you can see that this distance compared to this distance of 1, I have a slightly different scale for the convenience on my y-axis here. But I'm going to graph these key values, find at least one period here, and then I can always extend it for as much as I have made my graph reach out here horizontally. So I'll graph 0, 0. I'll graph pi over 16 square root 2. Now that's about 1.414. So about here, give or take. Pi over 8, 2. 3 pi over 16 square root of 2, so back down to about 1.414. And then pi over 4, 0. Do you see the first part of my wave for my the sine function? And then I'm going to continue this. 5 pi over 16 negative square root of 2. About like that, I guess. And then 3 pi over 8 negative 2. Well, that might be actually a little bit too far down, and then this would be about here, and then this would be about here, and then back to here. And you should be able to see with those points graphed my wave. Now I don't think I have to have every one of these key points. I think I can get away with just knowing my intercepts here, my x-intercepts, and my highs and my lows. But I'll go ahead and I'll try to sketch a smooth curve out of this. And there is one complete period of this graph. And what I would do is I would just continue finding my key values here. This is going to be up here at 2. This is going to be down here at negative 2. Then to 0, and then up to positive 2. And I can continue my graph here best that I can anyway. That wasn't very good. Let's see if I can do a little better than that. And that would be a pretty good sketch of the graph of f of x equals 2 sine of 4x. So, creating a table with key values and continuing the pattern, those are important things to be looking for. Now I have a bit of a change here because I'm also going to consider what we call a translation. Now you guys, we've done translations before. In fact, if you have the graph of y equals f of x minus h, okay, h not equal to 0 here, this is the graph of y equals f of x with a horizontal shift of, or a translation of absolute value of h units, which means, of course, that if h is positive, so it's going to look negative with a minus sign, but if h is positive here, we're going to shift it to the right. If h is negative, we're going to shift it to the left. This is sometimes called a phase shift. And I have a graph here. It's not exactly like this because I threw in where I'm subtracting a value. But notice here, I'm not subtracting it from x, I'm subtracting it from 3x. So I'm going to have to rewrite this. I am going to factor out inside the parentheses here this 3. So I'm going to have y equals the cosine of 3 times the quantity x minus, factor the 3 out of the 3x, it leaves the x. Factor the 3 out of the pi over 2, it's like you're dividing it by 3 because you're factoring it out, so that's going to be minus pi over 6. Now if you're not sure you did that right, distribute back, you should get right back to where you started. So in this case, I can see that I have a shift of pi over 6 units, and because pi over 6 is positive, remember x minus the value, it's going to go to the right. This is going to shift to the right here. So what I'm going to do first, just like I did in the last problem, I'm going to identify the amplitude. Now, the amplitude is 1 because A here is 1. So my amplitude, which I usually abbreviate just as AMP, is 1. And my but my period's been affected because of this value of B here, B that's times my independent variable. So my period here is going to be 2 pi divided by the absolute value of 3, which is 3, and my period is 2 pi over 3. So now when I go to graph this, I'm going to graph using, again, some key values. Now, you say, well, how did your key values affect it this time? Again, see what my 3x is? Those are the values that I had here for my 4x. These are the ones that I want. So I take these guys and I divide them by 3, because again, when I plug these in to here or into here, the first thing that's going to happen is they're going to get multiplied by 3. So I got to be careful here. Now, this is just going to graph y equals the cosine of 3x. It will not have the minus pi over 6 in. I'll do that at the end. I'm going to shift it to the right. As I mentioned, it's sometimes called a phase shift. I'm going to shift it to the right, pi over 6 units. So I'm going to do this in, well, no pun intended, but in 2 phases. First, I'm going to graph this, y equals the cosine of 3x. And I have these points, so I'm going to grab a different colored pen here. Let's try this purple looking one. So I have 0, 1, that's up here. I have pi over 12, square root 2 over 2, which is about 0.7. About 0.7, so I approximate. I have pi over 6, 0. I have pi over 4 negative square root 2, or about negative 0.7. Pi over 3, negative 1 down here. Then I have 5 pi over 12, negative 0.7. And pi over 2, 0. That's nice. Well, I believe I am almost completely done with my period here. 7 pi over 12.7. And then 2 pi over 3, 1. That should be in the ballpark there. I'm kind of eyeballing it best that I can. And you can see the curve here. I'm going to go ahead and sketch this in. And then this would continue. Notice here that the period is 2 pi over 3. So I have one complete half here at pi over 3. My amplitude is 1. So I have to be, let's see, back down to here by the time another pi over 3 happens. So if I was going to continue my graph here, it would look something like this. And the same thing this way. I would need pi over 3 here, so I'd have to be down to here. And there's my graph as far as I had my number line drawn out. Now, that's not the graph of this guy. That's the graph of this guy. He's in purple. What happens now, I'll get a green pen here, is that I have a phase shift now, or a shift to the right of pi over 6 units. So you see, look for those key points. The bottoms, well, not the bottoms, but where the like minimum points, where it bottoms out and where it peaks here, as well as my x-intercepts. Now look what happens. Pi over 6 units is this distance, right? So this is going to get shifted to the right, pi over 6. This is going to get shifted to the right, pi over 6. This is going to get shifted to the right. And I continue doing this until I have these points sketched out, and then I can continue, or I can come up with a graph here. Oh, that's not so good. There we go, a little bit better, not much. And as you can see, all the key points have been shifted over pi over 6 units. That's how I graph this. I don't do it all in one graph. I know students that try to do that. When you're first graphing these and you haven't done very much of this, that could be a problem. There's a lot of things to keep track of if you have multiple transformations. So if I throw in a reflection, or heaven forbid, if I throw in some kind of a vertical shift, which I'd like to show as well, you're going to have trouble keeping track of it. Do it in stages, one thing at a time, to make sure that you're coming up with a good graph. Here's a reasonably simple example. We're going to do some more examples. We have to practice this a little bit more because it's important to be able to analyze the graphs of these trig functions to really understand everything about the trig functions, all their little nuances and such.